Assalamu alaikum students. We covered different segments of freeway and the analysis, and there were two small things left. One was the example of a weaving segment, which I will start with now, and then afterwards I will explain how we can combine the flow rates and the densities of different segments to give you one level of service for the entire freeway. So let us start with the example of the weaving segment. You've already seen a step-by-step process of the analysis in the lecture, so I will be just applying it to this example. The example is problem 5.4 from the book, and we have a standard ramp weave segment. Now first of all, standard means this sort of a segment which has both ramps on the right hand side. Okay, entry and then exit, and both on the right hand side. Okay, free flow speed is given. Short length meaning the length from one ramp to the other, that is the short length. Let me make it here. So short length basically means from here to here, that is short length, and we represent it with ls. So this length is given. The main line volume meaning the volume which is on the freeway. Okay, so it's basically freeway to freeway. Okay, the person who will not use the ramp at all for entering or exiting. So those are 4650 vehicles per hour. Entering volume 875 vehicles per hour, exiting volume 730 vehicles per hour. The ramp to ramp flow is 175 vehicles per hour. People were coming from the ramp going to the ramp, and we have 10% trucks. It's a level terrain, and interchange density is 0.9 interchange per mile. So the first thing which I will do is I will convert all these volumes to their flow rates. So in order to do that, the equation which we have is this. Flow rate represented with small v equals volume divided by the heavy vehicle adjustment factor and the peak hour factor. Okay, and for the time being we are not required to calculate them per lane. Okay, so I'll just keep it as it is. Now we have different types of volumes. We have volume which is going from freeway to freeway. Let me call it VFF. Okay, so that is 4650. Now I need the heavy vehicle adjustment factor. For the heavy vehicle adjustment factor, the equation is this. Sorry for that. Okay. So the equation for heavy vehicle adjustment factor is this: 1 divided by 1 plus the percentage of trucks. Percentage of trucks for all cases is 10%, so 0.1 into the equivalency factor minus 1. Equivalency factor for level terrain is 2, so 2 minus 1. And if I calculate this value, it will come out to be comes out to be 0.91. Okay, and the peak hour factor is given as where is it? So the peak hour factor is not given, so I will assume a value of 0.9 for the peak hour factor. So 0.91 into 0.9, this will give me so it comes out to be 5678 passenger cars per hour. Okay, similarly I can calculate or convert all the volumes, all the given volumes, into their respective flow rates in passenger cars per hour. The factors will remain the same, only the volume at the top will change. So the values will be this. Okay, and you can see I have taken the volumes which were given, okay, for each case. So all the volumes are now converted to their respective flow rates in passenger cars per hour. Now using this, first of all I will calculate the minimum number of lane changes. This is the first thing which we do. As I said earlier, a standard ramp weave segment is this one. Okay, so when we have a standard ramp weave segment, the number of lane changes required to go from ramp to freeway are these. You can see the blue line. Okay, and the number of lane changes required to go from freeway to ramp are with the red line. So in total there are 2 lanes from which you can make the weaving, and these are minimum. So NWL equals to 2. Okay. So minimum number of lane changes will be calculated using this equation. So let me apply it to our segment. So after applying the equation for minimum lane changes, I got this. So the calculations were very simple. You just need to add the volume or the flow rate going from ramp to freeway and freeway to ramp, because both of them are multiplied by 1. So after this, the next step is to calculate the minimum weaving length. Now this is done because we want to know if our segment can be considered a weaving segment or not. Okay, so if the value of Lmax from here is less than the short length, then that means that it's a basic freeway segment. Weaving analysis will not be applied. So now you can see we need the number of lanes from which weaving can be done, that is 2, as I explained in the last slide, and we need the volume ratio then. Okay, so for the volume ratio I've already calculated the numbers. So using those numbers which we already calculated, the volume ratio comes out to be this one. So the weaving volume is the people who are going from freeway to ramp or ramp to freeway. Okay, and the total volume in the denominator. So you add everything which we calculated in the last slide, and the volume ratio comes out to be approximately 0.25. I'll move on to the next step. And the next step was to find out the maximum length up to which this segment can be considered as a weaving segment, and this is the equation, the Lmax equation. We have calculated volume ratio 0.25, and NWL, the number of lanes from which we can make the weaving, which is 2. So putting all the values here, I got the answer to be 4410.7 feet. Now the short length which is given between the two ramps is 1800 something feet. You can go back to the question and see. So we are in the weaving segment. If this Lmax had been less than 1850 feet, the given short length, then we would have said that this segment is not a weaving segment. Okay, then we can consider it as a basic freeway segment. So now we can resume with the analysis of the weaving segment. Okay, the next thing we need to do is find out the capacity of this segment, this weaving segment, and then check if we have the flow equal to or less than capacity, because flow reaches capacity, then we know the level of service is E. Flow is above capacity, then we know the level of service is F. So first of all we need to ascertain that what is do we have these extreme values or not. So to do that, first of all I will calculate the per lane capacity of this segment. The equation for per lane capacity is this one. Okay, so I have inserted the values here. So VR was 0.25 volume ratio, we already calculated, so 1 plus VR is 1.25. Okay, short length LS is given in the question 1850, so I inserted it here, and NWL, the number of lanes from which you can make the weaving possible, is 2. So 2 here, so per lane capacity comes up to 2105. Okay, then I need to calculate the total capacity for all the lanes, because there is a check available for that. So I will do it. Okay, so 2105 per lane multiplied by number of lanes. Now remember, number of lanes are 3 on the freeway, and then we have the additional auxiliary lane. So total capacity is for all the lanes, so multiply by 4. 3 the lanes of the freeway, and the fourth one the auxiliary lane. I can go back and see here 3 normal lanes. Okay, so these are the freeway lanes, can be 3, 4, 5, whatever, but you have to add the auxiliary lane, just keep this in mind. Okay, so the total capacity 8420. Okay, now there's a check that this capacity should not exceed these values depending upon how many lanes you have for the weaving. Now I have 2 lanes, so maximum capacity I can have is 2400 upon VR. So if I do 2400 upon VR, I get 9600 passenger cars per hour. Now the actual capacity which I have is less than this value, so I will keep this one with me for the rest of the analysis. If it had been more than 9600, then 9600 becomes a limit. Okay, then you will replace the value with 9600, and then you will use it for any further analysis. Okay, now since we know the actual capacity 8420, the total flow of my segment, does it exceed the capacity, or is it equal to the capacity? The answer is no. If you add the flow rates for everything, freeway to freeway, freeway to ramp, ramp to freeway, okay, basically I'm talking about these values. So if you add all the values, you are getting 7851 passenger cars per hour. This is less than the capacity, so I don't have level of service F. This is now certain, so I can move to the next step. Next thing we need to calculate is the number of lane changes per hour. Lane changes can be of 2 types. We can have lane changes which are necessary. Okay, so from the immediate lanes of the ramps, for people who are going from the ramp to freeway or freeway to ramp, and lane changes can be optional for people who misplace themselves in some other lanes and they just want to be on the safe side, or they were in the wrong lane and they want to change. Okay, so the weaving lane changes, the necessary lane changes can be calculated using this equation. We already calculated minimum number of lane changes in the first step, which was this one 1959, so I already know the value. So then short length is given. Number of lanes, as I mentioned earlier, 3 for the freeway and 1 auxiliary lane. Interchange density is given 0.9 interchanges per mile. This is given. Okay, so using all these values, I calculate the number of lane changes, the necessary 12370. Okay, one thing which I missed in this equation was the ideal capacity for the freeway. Now in this case, to find out the ideal capacity, we have seen a table previously. This was a table. Okay, ideal capacity for a particular freeway speed. Okay, or even if you don't want to use this table, we have seen how to calculate the capacity of a basic freeway segment. So you use the equation of a basic freeway segment to calculate the capacity. Okay, so this was the thing I missed. Okay, after that we have performed the check for the flow rate and the capacity, and we have calculated the lane changes which are required for weaving. Okay, so I've explained this, so let us move on to the next step. Now next step is to find out the optional lane changes. Okay, so we have the equation for that. So first of all, we need to calculate the intensity of the non-weaving lane changes. Okay, and this is the equation for that. And then on the basis of that, we will calculate the non-weaving meaning optional. Okay, the non-weaving or the optional lane changes. Okay, since the equations are very small, I will try to explain each and every parameter. So intensity of non-weaving is calculated like this. So we have the LS here, the short length, then we have the interchange density. Okay, I'm using this equation, keep in mind. And then we have the non-weaving flow rate. So non-weaving flow rate is basically freeway to freeway and ramp to ramp. Okay, so these are the two values which we calculated at the start. Okay, this value, freeway to freeway and ramp to ramp, these two. So this is the non-weaving volume or flow rate, and then divide by 10,000, it comes up to be 981. Now this, in this table, again sorry for the small font here, but if this value is less than 1300, we are supposed to calculate non-weaving lane changes using the first equation. Okay, and which I did over here. Okay, so this is again the non-weaving volume and the short length and the number of lanes. Okay, so it comes out to 1446 lane changes per hour. Okay, but you can see I have also calculated lane changes from this equation as well, the second equation, and this is because of this condition. The condition is that although the first equation may apply, you still have to calculate the second equation and check, apply this check. So when I calculate from the second equation, again this is non-weaving, okay, volume, and this is the only thing which I need in this equation. It comes out to be 3030. Okay, so this becomes like a minimum value. So if the first equation, even if I and W is fulfilling the condition of the first equation, still you will calculate values from both equations and you will compare between them. Okay, lane changes from the second equation is like a minimum value. So if the first equation is giving you a value lower than the second equation, you will take the value from the second equation. Like in this case, the value was 1446 from the first equation. Okay, now the I and W value fulfills the condition of the first equation, so I should be taking this value, but this value comes out to be less than the value from the second equation. So in that case, second equation will prevail irrespective of the I and W value, intensity of the non-weaving non-weaving scenario. Okay, so the total lane changes, the first one which I calculated, so this is a mistake here, let me correct the mistake first. Okay, this should be coming from here, which is 2370. Okay, so this 2370 for weaving people. Okay, the necessary lane changes, and we have 3030. Okay, so total will come out to be, the total will come out to be 5400. Okay, total number of lane changes are these. Okay, sorry for the mistake which I made earlier. Now we can move on to the next step. Okay, so now we have all the parameters. We need to calculate the speed of weaving volume and non-weaving volume, and then we will calculate, we will combine the speeds, and then we will calculate the density of the segment, and then on the basis of density we can decide what level of service we have. Okay, for the weaving volume, we will calculate the speed using these two equations. So first of all, I need to calculate W. Okay, so W is calculated using this. We have the all lane changes which I guess calculated in this step, the previous step, 5400. Okay, and then I have I need the short length as well. Sorry, this should be 1850 here. Okay, so you calculate W to 0.54, then you go to the speed of the weaving volume. It comes out to be you need free flow speed. Okay, so free flow speed is given for the freeway 65 miles per hour, and then we need 1 plus W, so 1.54 at the denominator. Now you can see here in the equation, free flow speed is multiplied by the adjustment factor, but for the adjustment factor we need the conditions. No conditions are given, so it will remain as it is. Okay, this will be like considered as 1. So the speed of the weaving segment comes out to be 47.47 miles per hour. Okay, and then for the non-weaving segment, this is the equation. Again, free flow speed multiplied by the adjustment factor, we take it equal to 1. Then minimum number of lane changes, and this is what we calculated at the first step here, so 1959. Okay, and then so 1959 here, and then 0.0048 multiplied by the total volume. Total volume includes everything. Okay, the one which we use for the check of capacity as well, weaving as well as non-weaving. Okay, so total volume divided by total number of lanes, as I have been saying, total number of lanes means the 3 for the freeway and the 1 auxiliary lane. Okay, so non-weaving velocity or speed comes out to 41.47 miles per hour. Okay, then for combining these velocities, the speeds, we have this equation. Okay, again, sorry for the small font. Can I increase it? Yes, I can increase it. Okay, so I need the weaving volume, non-weaving volume. Weaving is the people who are going from ramp to freeway and freeway to ramp. Okay, so those are 1959 vehicles. Okay, and non-weaving meaning the people who are going from ramp to ramp or freeway to freeway. These are 5892, and these values are coming from the flow rates which I calculated at the start. These flow rates. Okay, so all values are just there, I'm just adding them together. Okay, then in the denominator, each volume will be taken and divided by the speed of that particular volume. So weaving upon the weaving speed, so weaving volume is 1959 divided by weaving speed, which is 47.47, sorry. Okay, and this one for the non-weaving, then it should be 41.47. Okay, so after correcting the values, the new speed is this one. Okay, so this is a combined speed for both volumes now, weaving as well as non-weaving. Okay, and then when you calculate the density is from this equation. So total volume divided by total number of lanes, again 4, and divide by the speed which you got over here. So this is now 45.82 according to the new value. Okay, so the density comes out to be 45.84 vehicles per mile per lane. Now if you go to the density table, you can see that level of service is F. Okay, we have exceeded the density of 43 here, so level of service is F. Now you may ask a question here that why level of service is F, although we have already checked the capacity. Now level of service F can be because we exceeded the capacity, or because the density is now so congested the vehicles are finding it difficult to move. Okay, so in both cases the level of service can be F. Okay, so level of service F can be because the flow simply comes out to be more than the capacity, or the density is so high that it exceeds the highest permissible density. So in both cases you can have level of service F. Okay, so there's a level of service F on the basis of density, not on the basis of flow rate, so it can happen. Okay, now the last thing which I want to explain here is so we have discussed there can be different types of segments of a freeway, and you can have for each segment a different density, a different speed, and so on and so forth. Okay, now how to combine the level of service for the entire freeway. Even a particular type of segment can occur 2 or 3 times on the freeway. So you may have 2 or 3 weaving segments or 2 or 3 basic freeway segments. How to combine their values and calculate one level of service for the entire freeway. Now this is the equation. First of all, the final speed and density you have, the final speed and density after for example, in this case for a weaving segment we combine the weaving and non-weaving, right? Okay, so when I say the final speed, that means the combined speed of weaving and non-weaving, and similarly same thing for diverging and merging as well. So the final speed and the final density after combining for different flow rates of the same segment, you calculate the final speed and the final density. Okay, and then using those final values you will calculate the flow rate. So for each segment you will have one value of flow rate which is coming from the combined value of speed and density. Then you will take a weighted average for the speeds. Okay, a weighted average speed. How to do it? Flow of each segment multiplied by the length of the segment. Okay, and then you will do the summation for all the segments on the numerator. In the denominator, flow multiplied by length divided by speed. Again, I'm talking about the final speed. Okay, so you will get average speed, a weighted average speed for the entire freeway. So if you have 4 segments, you will do it for each segment. So it will be 4 terms in the numerator, 4 terms in the denominator. Okay, then you can calculate the weighted average of density as well. The weighted average density is, we need the density of each segment multiplied by the length of the segment, and then we need the length of the segment and multiply by the number of lanes we have in the segment. Again, number of lanes meaning all lanes total. Okay, so you can calculate the weighted average density. So this equation gives you weighted average speed, and this equation gives you weighted average density. And for the level of service, we need density. So after you have it, you can go to this table and find out the density, find out the level of service on the basis of density. Now this will be for the entire freeway. The freeway may have 10 segments, 12 segments. You have already combined all those segments into these two equations. Okay, so the main equation which we need for level of service is this one, but speed is also a helpful parameter for traffic engineer. So we also calculate average, weighted average for the speed as well. Okay, so I hope this was very helpful to you guys for understanding the analysis, mainly for the weaving segment.